In the final lecture for this section, your book talks about addition of velocities. So we talked about addition of displacements when we talked about following the pirate treasure map and how you could conveniently combine all of those travel 50 paces west and 30 paces northeast into a single final vector that will take you directly to your destination. Well, you can also do this with velocities. Velocities are vectors. Velocities can be added and subtracted from one another. And this is important, especially when you're talking about a relative velocity. Now, relative velocity is the velocity measured from a particular frame of reference. Now, a reference frame is the frame of reference a person chooses, but that reference frame can vary depending on the motion of the person. For example, if I'm driving in a car north on the highway at 65 miles an hour, my reference frame looks slightly different than if I'm in a plane traveling at a constant height at a constant speed than if I'm on the ground. So we need to be able to say, hey, I am in this reference frame, this is what I see. What would someone in a different reference frame see? Do my results and their results equal one another? So we can actually calculate that. In a simple example, and there's a video attached from Mythbusters. If you haven't watched Mythbusters, I highly recommend it. A wonderful science program where they blow a lot of stuff up. But they do a lot of scientific testing. So a truck traveling west at some speed, I forget the speed they use in the video, let's just say 60 miles an hour, fires a cannon backwards, horizontally, at 60 miles an hour. So from the reference frame of the driver. So there's a driver, hits the cannon, that cannon fires backwards at 60 miles an hour. Now that fires backwards at 60 miles an hour regardless of what the truck is doing. If the truck is stationary, the driver measures it firing backwards at 60 miles an hour. If the driver's moving, he measures it firing backwards at 60 miles an hour. So what would happen if you're just standing on the side of the road and this truck drives by at 60 miles an hour one direction and fires a cannon 60 miles an hour backwards? Well, I'll let you look at the video to see what ends up happening. But as you might suspect, for a person standing on the side of the road, the cannonball just floats there for a second, not even a second in midair, and drops like it was just dropped vertically. It has no horizontal motion at all. The ball, after it fires, just drops like someone let it go. For the reference frame of the person on the side of the road. Another example of this that your book talks about is dealing with airplanes. Airplanes measure their speed, their airspeed and direction through the air using fanciful equipment. But before the GPS came about, measuring ground speed was actually quite difficult. So let's imagine we have two cities here. One is directly north of the other. So city 1 and city 2. Now normally a plane flying from city 1 to city 2 would fly due north because that's where the city is. So the velocity of the plane, what you want is the velocity of the plane. Let's actually put the plane in the middle here. The velocity of the plane, or bumblebee as I have it drawn here, whatever, it should be due north. But what if there's a crosswind? What if, let's say, there's a wind in the area, in the vicinity, that's blowing west to east at 10 miles an hour? So the wind is blowing at 10 miles an hour. Well, if the plane then continues to point due north, what's going to happen is the plane will actually miss its target city, right? We have to add these velocities of the plane and the wind to see what the plane's relative velocity is actually going to be. So if the plane, this little object here is the plane, the velocity would normally be, say, 700. Actually, that's probably way too much for a plane. Let's say 400 miles an hour due north, but we add to that, not appropriate scale here, but I want to show it to you, 10 miles an hour wind. So the net velocity of the plane is going to be northeasterly. So the city, if it flies due north, the plane flies due north, it's going to follow the red velocity vector, right? So it's going to miss city 2. So how do you fix that? Well, you take that into account when you plot your course. So this is the vector you want, velocity vector you want, due north, in order to get from city 1 to city 2. You know the wind is going to push you to the right, so you subtract off the wind to get the velocity vector that you want, v-plane. So the plane actually has to fly to the northwest, a little bit to the west of north, in order to counteract the easterly wind to get the velocity vector, the net velocity, to go straight to land in city 2.